Welcome back. Next we'll consider angular velocity and angular acceleration in some more detail. So let's consider the rotation of a rigid body about an axis defined by the unit normal vector n, which is normal to the plane of rotation of point P. Point P has position vector r, and r makes an angle phi to n. The position of P is theta, and the velocity vector tangent to the circle v is dr dt, or r dot. Now the magnitude of v is ds dt, where s is arc length around the arc, which would be r d theta dt. Now r here is the radius in the plane of rotation of the point P, which is therefore r sine phi. So therefore ds dt equals little r theta dot sine phi, where little r is the magnitude of the position vector r, and theta dot is the magnitude of the angular velocity vector omega. So the magnitude of the velocity equals the magnitude of the radius times the magnitude of the angular velocity times sine of phi, where the angular velocity vector has magnitude theta dot and direction n. Now, if we make the construction omega cross r and take its magnitude, then its magnitude would be the magnitude of omega times the magnitude of r times the sine of phi, which is ds dt, which is the magnitude of v, as we found above. Therefore, given that v is perpendicular to the plane of omega and r, we can therefore write that omega cross r equals ds dt times the unit vector v divided by the magnitude of v, but ds dt is the magnitude of v, so therefore omega cross r is v. And so we now have a vector definition of the angular velocity omega in terms of the position vector and the velocity vector. So v, which is r dot, is omega cross r, where the magnitude of omega is theta dot. The acceleration a is dv dt, which from our previous slide is ddt of omega cross r. Applying the product rule is d omega dt cross r plus omega cross dr dt, which is d omega dt cross r plus omega cross v. And d omega dt is alpha, the angular acceleration vector, so we get that a is equal to alpha cross r plus omega cross v. So the angular acceleration alpha also acts along the axis of n, and its magnitude is omega dot or theta double dot. Now, making use of, again, v equals omega cross r, that gives us that a equals alpha cross r, and substituting omega cross r here, we get omega cross r. And so looking at the direction of this vector, we can see that these are the tangential component of a, and that this term here is the radial component of the acceleration. So let's consider the tangent and normal components of the acceleration of a point in the plane normal to the axis of rotation that is rotating in a circular motion about the origin. So our point is P with position vector r, and it has angular velocity omega, which is theta dot times n, where n is a unit normal vector perpendicular to the plane. The velocity v equals omega cross r, and omega is theta dot, so v equals theta dot n cross r, and the magnitude of v equals r theta dot, where r is the magnitude of the position vector r. Now let's consider the tangent and normal components of the acceleration. Again, omega equals theta dot n, and alpha, the angular acceleration, equals theta double dot n. And the acceleration vector, a, has a tangent component parallel to the circumferential unit vector e theta, and a normal component parallel to the radial unit vector er. So from the previous slide, recall that the acceleration a is alpha cross r plus omega cross r, which is a vector triple product. Now, recall from vector analysis, the vector triple product a cross b cross c equals b times a dot c minus c times a dot b. In this case, a and b are omega, so we get that omega cross r equals omega times omega dot r minus r times omega dot omega. Well, omega and r are orthogonal to each other, so this dot product is 0. Omega dot omega is the square of the magnitude of the angular velocity, which is theta dot squared. So therefore a equals theta double dot n cross r times e sub r minus theta dot squared times r times e sub r. Therefore, the tangent component of the acceleration is r theta double dot. That's because the tangent direction is the direction of n cross e sub r, which is perpendicular to the plane of the normal in r. So that's the tangent direction. So therefore, r theta double dot is the tangent component of the acceleration. And the normal component, a sub n, is minus r theta dot squared, which is minus r omega squared. So the tangent component of the acceleration is r times the magnitude of the angular acceleration. The normal component is minus r times the square of the angular velocity magnitude. Let's look at some special cases of rotation about a fixed axis. Again, omega is theta dot n, so the magnitude of omega is theta dot. The magnitude of the angular acceleration is d dt of the magnitude of omega, which is d omega dt, or applying the chain rule, d omega d theta dt, which is omega d theta. So when you need to integrate an angular acceleration as a function of theta, you can use this form. A special case would be a uniform rotation in which the acceleration is 0. For example, theta equals theta naught plus omega t. A uniformly accelerated rotation with a constant acceleration could be omega equals omega naught plus the magnitude of the acceleration times t, which would mean that theta equals theta naught plus omega naught t plus 1/2 alpha t squared, integrating. And then taking the square of omega, we get omega equals omega naught squared plus 2 omega naught alpha t plus alpha squared t squared, where alpha is the magnitude of the acceleration vector. And so that means that omega squared is omega naught squared plus 2 alpha times omega naught t plus 1/2 alpha t, which is omega naught squared plus 2 alpha times theta minus theta naught. So far we've considered rigid body rotations. Now let's consider a general rigid body motion, which would consist of a translation and a rotation. So point A with position vector r sub A has angular velocity omega, angular acceleration alpha, and point B, which has position relative to A of RB relative to A, which would be RB minus RA. So the velocity at point B, V sub B, equals V sub A plus the velocity of B relative to A, which equals V sub A plus omega cross R of B relative to A. so the rotation about A. Similarly, for the acceleration, we can write that A sub B equals A sub A plus A of B relative to A. This is A sub A plus alpha cross R of B relative to A plus omega cross R of B relative to A. So in other words, the most general motion of a rigid body is equivalent to a translation defined by the motion of a reference particle, in this case A, and a rotation about the fixed point A. We're now ready to apply the equations of motion to a rigid body with center of mass G with respect to a reference frame with origin O and coordinates x, y, z. External forces acting on the body are F1, F2, F3, and F4. Newton's laws tell us that for the motion of the center of mass G with respect to the reference frame, that the sum of the forces must equal the mass of the body times its acceleration. At this point, it's useful to define a new reference frame with its origin at G, we'll call x prime, y prime, and g prime, for the motion of the body with respect to this centroidal reference frame. The external forces also give rise to moments about G, whose sum is equal to the rate of change of angular momentum, L dot about G, which is equal to I, the moment of inertia, times the angular acceleration alpha. So this system of external forces is said to be equipolant to the system consisting of ma and I alpha. Now let's consider the special case of a rigid body in plane motion about an axis through its center of gravity perpendicular to the page. With respect to a centroidal reference frame, particles pi in the body have position vector ri and velocity vector vi, and they all have angular velocity omega. The angular momentum of this slab, L sub g, equals the sum from I equals 1 to n of ri prime cross vi prime times delta mi, where delta mi is the fraction of mass of the whole body associated with each particle. So therefore I equals 1 to n of ri prime cross omega cross ri prime times delta m sub I. But since omega is constant, this equals omega times the sum of ri prime squared times delta mi, which equals I omega, where I is the mass moment of inertia. Therefore, the rate of change of angular momentum, L dot g, is equal to I omega dot, or I alpha. So again, we have a body with mass m and external forces acting on it that is equipolant to a body with forces ma and moments I alpha about g. We can therefore consider that the combination of these systems of external forces minus the inertial force and the inertial moment must be in balance. They must all add to zero. So this is like a free body diagram for a system that is in motion and accelerating, and we sometimes refer to this as dynamic equilibrium. So D'Alembert showed that one can transform an accelerating rigid body into an equivalent static system by including the inertial force and the inertial torque. The inertial force must act through the center of mass G, but D'Alembert found that the inertial torque can act about any point in the body with the exact same result. This makes the analysis simpler than what we've seen to date, where we've required that the inertial force and the inertial torque must act about the center of mass. So now we can use the free body diagram approach that we use for statics for problems in dynamics as well.